Today we get to the important one, the discrete Fourier transform. It's a transform that gives us stuff that is discrete both in time and in frequency. So this is just the slide from the last few lectures. We've been staring at this slide with some pain and suffering. And what this slide does is it tells you how you go from a continuous time signal to a discrete time signal and what happens in the frequency domain. Okay, so what happens when you go from continuous time to basically discrete time is you end up with a discrete signal that you can save on a computer. Wonderful. But the spectrum here, the spectrum is continuous. Okay, so a discrete signal has a continuous periodic spectrum. Okay, and that's what we got when we did the DTFT, the discrete time Fourier transform, which is just the Fourier transform for any discrete signal. It's just the same thing as the Fourier transform, no approximations, it's just for discrete signals. So we end up with this spectrum that's periodic and continuous. What we are going to do today, the aim of the game is to get something where not only the time domain signal is discrete, but also the frequency domain signal is discrete. And unfortunately, it won't be exact, but we'll be able to do it. And this is called the discrete Fourier transform. And the nice thing about that is the moment I'm in that space where both the spectrum are discrete with little dots and my signals are discrete with little dots, then I can do everything on a computer with simple like Python or microprocessing functions. Okay. The problem with a continuous signal is I can't store it on a computer. I can't do anything with it. So what I want is I want this to be discrete and that to be discrete. Okay, we already have this as discrete. So we're going to figure out how to get a discrete version of the green signal of my continuous spectrum. The strategy we're going to follow is this, and this will only make sense as we go through, so I'll go through it pretty quickly. A discrete signal has a spectrum that's continuous and periodic. A discrete signal has a spectrum that's continuous, green line, and periodic, it repeats. What we will do now is step one, okay, step one is actually done already. We've done this one. What we will do now is we will sample the spectrum. The roadmap is actually going to be, we've sampled signals. Now let's pretend we have a general signal, and then we're going to sample the spectrum. Then what we're going to do is we're going to sample both, okay? And then we'll see that we can do both, but it comes with some caveats, okay? And then we'll do a hack in order to get around those caveats, and then we'll get to the DFT, the discrete Fourier transform. You guys know how to sample signals in the time domain. We've done that. That's everything we've done up to now. Basically multiply with the impulse train, the time domain signal. What we do on this slide is we sample in the frequency domain. Okay, so just pay attention here. Here we've got a continuous time signal, okay? And here we've got its spectrum. Boom. I want to sample this thing. That's where we want to end up today. So how do I sample this? In the frequency domain, I multiply this thing with the impulse train. There's little impulses at capital F, at 2F, at 3F, 4F, 5F. So it's like what we did in the time domain when we sampled time domain signals. Now we're just sampling the frequency domain. If we do this, we take this signal, we multiply it with this, then we get this sampled spectrum here at the bottom. We get a spectrum, but it's been sampled at these discrete points, every capital F hertz. Multiplication in the frequency domain corresponds to convolution in the time domain. Everyone with me? Yep. An impulse train in the frequency domain corresponds to another impulse train in the time domain. And if these things are separated with capital F, then in the time domain, these things are separated with 1 over F. And there's one at 2 over F and 3 over F and so on. Okay, awesome. We take this thing, this continuous signal, we convolve it with this impulse train, and what we end up getting is dunk, 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 dunk. What we see here is that a periodic time domain signal has discrete frequency components. Okay, is this the DFT? No, because this thing is continuous. I can't store this on a computer, sad face. Okay? But we're halfway there. We got a sampled spectrum. Okay? Does that make sense? Quick question. Do you know what the strengths of these impulses are? Actually, this is just the Fourier series. Okay? So remember, before Fourier transform, you sat in a math class and then you learned about the Fourier series, which was really just a way to take a periodic signal and break it up into its frequency components. Okay, remind yourself of this. It's not super important. This will be self-contained. But the strengths here will be are actually given by the Fourier series. So what we now know is two things. We know a discrete signal has a periodic continuous spectrum. If we're discrete in time, then we have a continuous spectrum, the green line. Okay? If we have a periodic continuous signal, then we have a discrete spectrum. If I have a periodic continuous signal, then I have a discrete spectrum. Okay? So what do I do when I want both of those things? It's pretty cool. All I do is I get a discrete periodic signal. Okay? A discrete periodic signal will have both spectrum and time will be discrete. So basically what we're going to do is we're going to sample in both time and in frequency. So let's start by sampling in time. Quickly, how do I sample in time? This is my time domain signal. This is x of t, and this is the frequency domain of that signal, x of f. How do I sample in time? I multiply this thing with just shout it out. Impulse train. Absolutely correct. Okay, so we will have impulses, tunk, tunk, tunk. At minus t, we will have an impulse. At 0, capital T, we will have an impulse. At 1t, we'll have an impulse. At 2t, we will have an impulse. And at 3t, we will have an impulse, and so on. The result of this is a discrete time signal. This is not the signal. This is just my hint for where my impulses will land. So at time t, we've got one of these. At time 2t, 3t, 4t, and so on. Okay, so that's my discrete time signal. What happens in the frequency domain? So now I've sampled in time. What happens in the frequency domain if I sample in time? I convolve this thing with an impulse train, and my impulses sits at, if this is t there, then my impulses sit at 1 over t, at 2 over t, which is somewhere here, at 0, at minus 1 over t, and so on. So the result of that in the frequency domain is that I get a signal that looks like this. And what's happened is this thing has been copied where the impulses land. Okay, so I get this, and then at 1 over f it goes up, and here at minus 1 over t. At 1 over t it goes up, at 2 over t it goes up, at minus 1 over t it goes up. Okay, we've sampled in time. Now what we'll do is, step 2, we sample in frequency. Okay, so how we sample in frequency is we multiply this thing with an impulse train. And that impulse train sits at, let's call it capital F. That's minus F, that's minus 2F, dunk, 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 at 0, at F, at 2F, at 3F, and so on. And the result in the frequency domain is then very nice. What I end up having in the frequency domain is, let's draw it like this, pretend that this is the same as the plot above. Okay, and what we now get is that's not actually the sampled signal. The sampled signal is I basically hit this at minus F, minus 2F, at 0, at F, at 2F, dunk, 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 and so on. Okay, and the same thing here. So what is this? This is wonderful. This is a sampled spectrum, which is what we are looking for. This is the aim of this game. And what do we get in the time domain? What happens in the time domain when we do this? Okay, so in the time domain we're convolving, because here we've got a multiplication. So in the time domain we've got a convolution, and then we're going to convolve with an impulse train. Okay, And those impulses will sit where? 1 over f, that's right. So you'll have a little impulse at, let's say here, at 1 over f. You'll have one at 2 over f. You'll have one at 0. You'll have one at minus 1 over f. Okay, and remember this is time here on this axis. So what we're going to get here is, what convolution does is it takes copies and places that at minus f, 1 over f, at 1 over f, at 2 over f, at 0, and so on. So what we're going to get is we're basically going to get a signal that goes like, okay, and then at 1 over f, and at 2 over f, okay. This is not the signal, right? Because the signal is actually these impulses. So what we get is this, 0, 0, 0, this, and so on. Just imagine that it's more beautiful than what I'm scribbling here. And this point here will be at 1 over f. Okay, this point here will be at t, and at 2t, so on. Oh, sorry, thank you. Okay, excellent. I made a mistake. Can you see the mistake? Thanks. Okay, this 1 over f. I was testing you guys. That's rubbish. I was just a dumbass. Okay, so the 1 over f actually sits, wait, where does it sit? It sits here. Thank you, excellent. And then the 2 over f, 2 over f sits there. Okay, did everyone see my mistake? Thank you. Okay, and obviously we have the signal also going on that side. Okay, thank you. Okay, now we've reached the point where we're very happy because we have a discrete time signal that goes with the discrete spectrum. I can save the strengths of those impulses either for frequency or for time on a computer. So what we've proved is a periodic discrete time signal. So if we have a signal that's discrete and repeats, then the spectrum will also be periodic and discrete. Are we done? Yes? Yeah, we're done. No, we're not done. Because I've now taught you how to deal with periodic discrete time signals. But sadly, many signals that I want to deal with is not periodic. Okay, so what do I do here? Okay, fine, I've solved it for periodic discrete time signals. What do I do if I have a signal that's not periodic? How do I deal with that? Okay, so most signals won't be periodic. Most signals won't, like here we were lucky, this thing is limited in time. Most signals won't be limited in time. It goes on and something happens. So for those cases, we're kind of screwed. Yes? Sad face. Okay, so how do we hack this? If I have a signal like this one, that I want to sample or deal with, I'm just going to hack it. I'm basically just going to window that signal and then repeat it periodically and turn it into a periodic signal. Okay, and that is actually what the DFT does. Okay, now windowing is a lot, and I'll recap this in a second. Windowing is of course a little bit dangerous. So if I just take a window of a signal like this, a square window, then okay, fine, I'm cutting out this signal here. But what happens in the spectral domain if I multiply with a window? If I basically zero out everything up to some portion and then I cut out everything after this. This is the hack I'm proposing. So what happens if you do this hack? I multiply with this window. That corresponds to convolution in the frequency domain. What am I convolving with in the frequency domain? What's the Fourier transform of a pulse? A sinc. This pulse is shifted, so it's not around the origin, so you need to, the phase goes a little bit haywire, but you're right, you're convolving with the sinc. Okay, let me just draw the magnitude of that sinc. So you have basically you have the first blob, and then the second blob, and the third blob. Okay, and the same thing here, something like that. Okay, and it goes on forever and ever and ever. Okay, quick question. This is a little bit tricky. If the width of this is, I don't know, let's call it A, then where's that point? 1 over A, excellent guess, also correct. Okay, so 1 over A, that one is a 2 over A, and so on. Okay, cool. That will become important in a second. So what happens if you have a sinc convolve with this thing? I don't know is the answer, but like intuitively, I'm just going to draw this signal as a dotted line here at the bottom. So what's going to happen, it depends on the width of the sink and what the sink looks like. But basically what you're going to get is you're going to get little bumps in this signal. That's fine sometimes. And this is actually what the DFT, you will have to window things. You will have to truncate it, and it will cause bumps, and it will make you sad. How can I make the bumps smaller? What happens if I make my window very big? What happens if I make a really, really big? That's spot on. So as the sink, like basically as this goes long, if you take a very long window, then what will happen is this point will move in, and the blob will become higher and higher, okay? And so in the end, like if you take an infinitely long window, you're just convolving with the impulse. And convolving with the impulse is super nice because it does nothing, okay? It might move something, but in this case it doesn't because the impulse is at the origin, so it doesn't actually do anything. Yes?
Isn't that defeating the purpose of windowing?
Yes, that is exactly right. So we live in a broken world, which you are highlighting, and you're exactly right. So you can't do your trick, okay? But take a long window, as long as you can, practically speaking, okay? Okay, so just going back to the cheat sheet of our route, what we figured out was discrete signals, periodic continuous spectrum. Discrete spectrum, periodic continuous signal. To get both, we need a discrete periodic signal, done. If we don't have both, then what we do is we window and basically take that window and we repeat it over and over again, okay? And that is what the DFT does. So we will now go through all of the DFT steps. And along the way, as we're going through the DFT steps, we'll derive the DFT equations as well. So here we've got a signal. It's a continuous time signal. Here we've got its spectrum. Okay? Step one, we sample. Okay, so we take this thing and we sample it. It's going on until infinity, but we can sample it mathematically speaking. Okay, so we sample. What is the transform that you love and hate a little bit now? When you sample, what do you get? You get the discrete time Fourier transform, which is not the same as the DFT. The DTFT is just the Fourier transform of a sampled signal. Okay, and that is why we went through the pain and suffering of deriving the equations for that, is because we need this one single equation on this slide. Okay, and what happens when you sample is you can represent the spectrum here as the sum of a whole bunch of complex exponential things. H n t, I could have written there, that's just the same as Hn, which is just the strength of the samples at those points, okay? Times e to the minus j2 pi f n capital T, the sampling period. If this equation freaks you out a little bit, you've got a bit of homework to do. Go and watch the video on the DTFT. This equation is just an equation for the green line here. Okay, wonderful. We've sampled. Step two, window. Okay, we live in a broken world, so we can't keep all the samples up to infinity, so we need to window it. Okay, and what you do now is you get a new spectrum, the windowed signal, which, what does that do? It adds a little bit of a blobbiness to my signal. So windowing in the time domain, I'm multiplying with in this case, a rectangular window. That means in the frequency domain, I'm convolving with a sink, okay, which I'll just call WF. The cool thing is, how does this affect this equation here? All that's happening now is we still have h of nt here, or h of n, but we're zeroing out all the samples after some window, okay? So I'm going to write the sum here, and I'll keep h of nt, and I will multiply that with e minus j2 pi f n capital T. What should I write on the summation here? Spot on. It goes from 0 to n minus 1. Okay, and that's exactly right. So this is super nice. because I can't actually ever practically do minus infinity to infinity, but I can definitely count to 10 if I have 10 samples. Okay, so we've windowed. So the next slide just has the window here at the top. Just copy that from the previous slide. We have our sinc function here, rectangular window, and we've got this equation here. Wonderful. Step, I don't know how many, step 2 or 3 or 4, something like that, is we periodically extend the signal. The problem is this spectrum here is continuous. We want it to be discrete. To get it discrete, what we'll do is we'll take this thing and periodically repeat it from minus infinity to infinity. Just create copies of it periodically. And that will cause our spectrum to become discrete, which is exactly what we want. So now we get some new periodic spectrum, HP of f, and this thing is just equal to h, the windowed spectrum, multiplied with some impulse train. Okay, going from minus infinity to infinity. So in the frequency domain, I'm multiplying with the impulse train, with the impulse there, and so on. Okay, and so what I have is I basically have impulses that are moved multiples of this capital F. Now capital F is like capital T in the time domain. It's like the sampling period in the frequency domain. Okay, and it tells you basically, so this impulse will sit at F, this one is at 2F, 3F, and so on. So the distance here is capital F. Okay, now there's a little design decision that we will make, but it's not really a decision because the DFT just tells you what decision to make. And the decision we make here is that we make sure that the distance between these impulses is chosen in such a way that this thing repeats perfectly where we ended up after windowing. So basically what I'm saying is I make sure that F, remember F actually determines where this impulse will sit. I choose F in order for the next period to start exactly where I ended before. Okay? Does that make sense? Not? Okay, awesome. So we make sure that 1 over F, 1 over this capital F, is equal to what? Okay, 1 over F in terms of, like, it should be something with time. Okay, I'll show you on time where capital T is. Capital T is here. Okay, where do I want my impulse to sit? Do I want it to sit there, there, or there? Say stop. Stop. I want my impulse to sit there. Okay, and this, so this is a T, this is a 2T, this is a 3T, 4T, 5T, 6T, 7T, and then, so this is basically the nth minus 1 sample. This is sample n minus 1. And we want that impulse to sit right after that. And in time, that position will be nt. So if I have 8 points, then I want this thing to sit at 8 times the sampling period. Does that make sense? This is 0.0, this is 0.1, this is 0.7, and then we want this thing to sit at 0.8, which in time is 8 times the sampling period. Is everyone happy? Okay, and now we are at the discrete Fourier. I don't know how to pronounce that properly in French. Someone with a French background tell me how to pronounce that thing. Fourier. Just say that again. Fourier. Fourier. Okay, the proper Afrikaans pronunciation is Fourier. So we say it that way. Okay, we're now at the Fourier transform. Yippee! Sorry, we're now at the discrete Fourier transform. Okay. So what do we want in the discrete Fourier transform? We want discrete time samples. And I have that. That's easy. My discrete list of time samples that I can save on a computer, that's just equal to basically what happened at capital T, at 2T, at 3T, and so on. So that's just this little equation that we had before. You just take the strengths of these impulses at those like discrete points in time, at T, at 2T, and at 3T. So H1 is equal to the continuous signal, the strength of the sample at time step capital T. We've got discrete time samples. Woo! Okay, now we want discrete frequency samples, and we'll just do the same thing. What we're going to do is we're going to save the strength of these impulses, okay? And we will call that H capital K, okay? And H capital K is really like, so capital H, I don't know, 2 is just whatever happened on the basically on the green curve here, at 2f. Okay, so it's basically the same thing as the time domain. Little square brackets means this. Now in the frequency domain, square brackets just means like go to the second thing the second point that we sampled in the frequency domain. Okay, so what I need basically, so if it's h2, so h0, 1, 2, then I need this height, the height at that point. The height at that point is actually given there. So I can just take this equation. This equation tells me what that green line looks like. And it's not a height, it's a strength. But here it is a height. So the strength here gets given by this height here. And that height I just get from this equation. All I need to do is I basically just substitute in k times f. So if it's 2, then I look at 1, 2, and I get the height there. Okay, this is the, for sample 2, this is the height I read off. Okay, and I get that from this equation. So all I have to do is I just, everywhere where there's an f here, I just replace that with kf. H. Okay, I could write nt, but there's a little shorthand for nt, and that is just square brackets hn, okay, times e minus j 2 pi, and everywhere where there's an f, I now replace it with k, capital F nt. Okay, we're almost there. Now, the cool thing is, because we made this decision of where one f lands, this actually simplifies. So let's just do that. So k capital Ft, that is just equal to, you do some grade 1 mathematics here, k times 1 over ntt, and the t's cancel out. So you're just left with k over capital N. Okay, so we can simplify this even more. 0 to n minus 1, hn e minus j 2 pi k over n little n. Is that right? That's the DFT. That is the DFT equation. The DFT, it's just that same equation that I just had. The DFT tells me what I should do to a discrete signal of n points in order to get basically the sampled spectrum. If we go back to this slide, we've got n points in time, which are associated with n points in frequency. Okay? Capital N points here, capital N points there. And the DFT tells me what should I do to go from the n points here into the spectral domain. There's also a thing called the inverse discrete Fourier transform, which looks very similar. You can derive it this evening in the bath with a bit of red wine or Castle Light. You swirl it around and then you derive the inverse discrete Fourier transform. So if you have HK, I can go back to the time domain signal. The derivation is easy but long. Okay, so the derivation, if you're really keen and you've poured a very warm bath, you can read through the derivation. Okay, so the DFT gives you n pairs, and their friends. And we can save, these are numbers that I can save on a computer, these are numbers that I can save on a computer, and now we can actually calculate Fourier transform-like things on a computer. The DFT isn't perfect, right? There were a number of things that went wrong, and we'll look at that on Wednesday.